mode, and you can also hide.
Okay. Okay. Welcome everyone. It's a pleasure to be here. Also, like when Professor Chaya pronounced my name, he actually pronounced it correctly, which sounded wrong to me. So I had to kind of realize that. So actually I was giving some point a talk at CMU, and essentially so the host, who was not Polish, actually pronounced my last name correctly, and then I just started by saying welcome, my name is Aleksander Mądry, and completely kind of undone his effect. So he was actually spending a lot of time practicing it correctly, and then I kind of undermined it. So Mądry is one way of doing it, the proper way of doing it, but usually I just go with Mądry. So anyway, it's a pleasure to be here. We have beautiful weather, so I'm not sure why you are sitting here, but since you are sitting here, so let me tell you a little bit about actual machine learning, and something that kind of, on one hand, I find very simple and kind of, there will be a lot of relatively to follow. But actually, the more I think about it, the more I see on the one hand, like how this really touches on some kind of root of the problems with machine learning robustness. And also, I do feel that there is some mathematical structure kind of, kind of hiding behind what I'm talking about, but I have not yet succeeded in showing that. So maybe one of you will. Okay. And actually, like it does connect to even to Fourier analysis, but I will not. I will just mention it in one place. So everything fits. Okay, so let's talk about data models, and of course, the people who really deserve the credit for this work are the students, who actually they are the brilliant minds behind much of what I will talk about. Okay, let's get started. Or can we get started? Something froze. Oh, I know. Okay, so this click works, but this doesn't. Okay, well, no, it just, okay, let's see. Oh, now it works. Okay, something, I guess it was a bit frozen. Okay, so the point of start here is kind of starting to like try to like, look at, how we tend to think about the machine learning pipeline nowadays. Okay, so in particular, if you are kind of reading the news and reading about the deep learning, but again, machine learning in general, kind of the picture, the kind of the cartoon picture you will have will be, oh, you have a bunch of like data points, the training set, which is some images, and then you essentially use these images to train some model on them. Okay, and what you are getting as a result is a model. And kind of, if you look at much of work in machine learning, it really focuses on this model that we train with the data. And this makes sense. First of all, it's kind of that's what we needed for a long time to actually develop sophisticated enough architectures for our models and ways of training them to get things even like get something to happen. But also, to be honest, it's actually easier to kind of intervene and kind of experiments with the models, because you could just change something and then you retrain the model and see if whatever you cared about happened or not happened. So that kind of makes it easier to experiment with that. So this was the typical focus. It still is the typical focus of where the most of the energy of machine learning research is kind of homing in on. However, the point I want to make today, and also much of what I will talk about, is that actually it's really important for us to start to pay more attention to the data that actually goes into these models. Like in some sense, what really happens is that the way the model sees the world or solves the task is really inherited from the data. That's what machine learning is about. You are supposed to learn from data. And kind of what turns out, and this is kind of a thing that was a journey of my own, is that like, as well, is just like I realized that more and more of the behaviors that we would kind of attribute to the model, they actually kind of come down to what data the model was trained on and what insights it got from there. Okay, so why does data matter so much? So I already said it briefly, but let me kind of let me say more. So one of the key reasons and thing to realize about our current particular deep learning model, like it's not true about all of the models, but most of the ones that you are likely to encounter, what it says there is that really what these models are excellent correlation extractors. Okay, the way they really work is by whenever they sift through the data that they are trained on, what they really are trying to figure out is a bunch of features, some kind of patterns in data. And then for each of these features, they see how much often they, let's say, they correlate with the label being dog versus the label being cat. And that's all they really look for. Again, they are extremely good at finding interesting features that have this kind of correlate much more with one thing versus the other. But in the end, the way they predict is by whenever they see new input, they see what kind of features this input has and looks at the corresponding learned correlation between that feature and whatever class is the correct class, and then whatever is the most likely class based on that. That's what the model does. And on one hand, kind of this is actually brilliant, and in some sense, it really allows us to do a lot of really cool stuff with machine learning. Like all of the deep learning stuff you have seen, it's just essentially this paradigm taken to large scale and in sophistication. But this way, if this is how our models work, this has some implication, in particular from the point of view of data. So, and the key issue here is something that anyone who hears word correlation already should think about is spurious correlations. Okay, so not everything that that is correlated is in any way actually connected in a causal way. So there are some funny ways of doing it. And again, if you work with data, you can find all of these like strange correlations that don't really make sense, but based on correlations should make sense. Okay. And so that's fine. So there are correlations that are spurious. Not all of them are actually corresponding to some causal characteristic. But then you might ask yourself, okay, so why is that a problem? Well, it's a problem for many reasons. The first and the most obvious one is that like if all that my model is doing is looking for correlations, then such correlations can be planted. Okay, and essentially I can manipulate the behavior of the model based on that. Just a simple example. Imagine I have a training set for training cats versus dogs. And imagine what happens if I now go over this training set and I modify it. And for every picture of a dog, I just make the top left pixel orange. For every picture of a cat, I will make top left pixel blue. And I will take this as my new training set. What will happen if I train my model on this new data set? Well, you can guess what happens. It will realize, well, that's a simple task to solve. To decide whether this is a cat or dog, I just have to look at the color of this pixel, and that's all I will pay attention to. Okay, so essentially what will happen is that like suddenly by kind of manipulating, planting this correlation in the data, I essentially I hijack the whole decision making of the model because they just realize, oh, I found perfect correlation. So what more could I ask for? This has to be it. Okay, and as you can imagine now, if you start becoming a person with some bad intention, this can be exploited. Okay, in particular, Tom here spent quite a lot of time thinking about that. So clearly, he might not be that good of a person if he's thinking about this. But this kind of one way of militarizing this is so-called backdoor attack, in which we exactly use the ability, a bit more sophisticated ability to to manipulate part of the training data to essentially have a full control of the model. So just to give you another example, so imagine there is some face recognition task and there is an original training set, and then for some reason, I would like to plan the correlation in which whenever there is a particular type of red glasses that that the person on the picture has, then the label becomes Chris Hemsworth. Okay, so imagine I do such intervention. What can I accomplish in this way? Well, very important tasks. Because essentially, next time if someone trains the model on this data set and puts my face into there, and I will put these glasses on, then I will be classified as Chris Hemsworth. So clearly, there are some important things we can accomplish this way. By the way, I gave it because you can see, of course, this is just a joke, but you can see that if you have this automated passport control gates happening, you can imagine if you someone puts some funny glasses and can be passed off as a different person. So this sounds like a serious thing. I actually gave a version of this talk to DHS and told them about this this potential problem, and they said, don't worry, we are not even using machine learning there. We are so much behind. So essentially, if you ever worried about security of our nation, you don't worry, they've got you. So anyway, so that's one way. But this is only this may be of concern if you were really concerned about some people wanting to mess with our data. But unfortunately, even if no one tries to mess with our data, it turns out that this is still a problem because this kind of spurious correlations, they actually exist already in the data sets without our explicit intervention. So just the funny example here is that we, again, as many research groups in this area, we essentially, study a lot of Imagenet. And one thing that you will realize once you stare enough into Imagenet, you will realize that some of the pictures of the pets, dogs and cats, they have bow ties on them. Why people put bow ties on the animals, like that will remain a mystery to me, but it is a fact of life that they do. However, also what actually happens, it seems that like actually they tend to put bow ties on cats more so than on dogs. Again, why? I have my theories here, but I will not disclose them depending on which side of dog versus cat you are. But essentially, that's also a fact. But now, what is the implication of this fact? Well, the implication of this fact is that now the presence of a bow tie actually can become a feature that actually correlates with, well, more with the picture being a cat of a cat versus of a dog. So suddenly, the presence of a bow tie in a picture makes it more likely that this is a cat. So we should start to be a bit worried about that. And kind of, it's not only that these things happen. In some ways, actually, they happen even more so because the way we create our data sets kind of gives rise to this kind of spurious correlations. Because typically when we think about creating data set, the picture we have in mind is the following: that okay, there is some real-world images that we kind of have taken, and then there are some expert annotators hired to look at every image and correctly classify it to whatever class we wanted. We wanted to have this images classified, so we get these perfect annotations. And then, of course, we have some meaningful benchmark that we train our model with respect to maximize. And then we have these beautiful machine learning models that do exactly what we intend them to do. Okay, well, that's the ideal world, but it's not possible for many reasons. But one of them is scalability. Like, we will not be able to create as large data sets as we are using with this approach. So what do we do instead? Well, we do instead of like the next best thing. Okay, so what we do is saying, well, we don't really take pictures in the real world. We just like scrape them from somewhere. It's like found data. And then we kind of don't really have like expert annotators. We kind of use some kind of automated like a crowd labeling to get some labels. These labels are not perfect, I can tell you that, and there will be much more to be said here. And then we kind of look for some easy to optimize benchmark, and that's the machine learning we actually get. Okay, and all of the data sets that you might have heard of, the big ones, they kind of were created this way. And again, the good thing is that this kind of still gives us really cool stuff, but this also bakes in these unwanted correlations. Okay, so just to give you an example, an Imagenet. So when I ask, okay, so we all in this room know what a fish is, but if you actually didn't know what this word means, or if you kind of completely didn't know what, like you were just really like, this poor model that doesn't know anything about the word except inferring from data, what actually would fish mean to you according to Imagenet? Well, one important piece of information is that Imagenet was built based on the images scraped from social media. Flickr. I know that probably many of you don't remember that, but that was a thing at some point. And essentially, so this think of this is like pictures taken from Facebook. And now think about it. How does fish look like if you wanted to learn of how fish look like based on Facebook images? Well, first of all, most of the Facebook images hopefully doesn't have fish, but some of them do. But like, what kind of fish will we see? Will it be people kind of diving into the oceans and rivers and taking pictures of of fish in their natural habitat? Not really. Most of the things you are getting is people kind of having caught a fish and wanting to show to their friends what they caught. So now, if that's the kind of pictures of fish that you are getting, and all you are working on is based on correlations, well, you will learn interesting things about fish. And in particular, you will learn that actually, like, the fish involves a human doing something like that. So you can even erase the fish or put some other object here. It still will believe this is a fish because that's the kind of that's the kind of inference it made. Similarly, it learns that the natural habitat for crab is a plate, and many other kind of delightful things like that. But still, this is just fun. This is Imagenet, like this is just for fun and giggles. Unfortunately, this is not just Imagenet. So other kind of examples are, for instance, in the medical domain. So I don't know if you remember, but maybe like three years ago, everyone saying goes, oh, maybe even 5 years ago, essentially like radiologists will be out of jobs because of machine learning. Essentially, like you will have these models, we train these models that they get an X-ray and they will do a better diagnosis than the radiologist and do it for free and at scale and so on. Well, kind of. So my favorite example of what might go wrong here is just the following. So there was a study of they wanted to train a kind of a model to recognize if someone has a tuberculosis based on the X-ray. And they trained the model, and it was great. It was like validations were great. Like essentially, it looked wonderful. until someone kind of looked a bit deeper and actually tried to understand, like, how does the model make its decision? And what they realized that the model pays a lot of attention to one detail about the X-ray, namely the type of X-ray machine that took the image. Okay, so how on earth would it matter for anything? Well, it turns it actually matters, because then people realize, think, wait, so the way we got the positive example that tuberculosis is a rare disease in developed countries. So the way we got the positive examples of tuberculosis is by kind of taking the data from developing countries. But the developing countries tend to have older X-ray machines. So suddenly you have this kind of very nice feature that tells you what is the right answer, that actually doesn't really tell you what is the right answer. So that was the problem there. Another example was there was an app that was supposed to recognize, you take a picture of some change on your skin and tells you if it's malignant or not. Here, like, the ruler was actually the kind of the spurious feature, because essentially, like, if you go to a doctor and they take a picture for clinical reasons, they actually will put a ruler next to it, because just for reference. So essentially, like, if there is a ruler, there is much higher chance that it's actually something bad, because that's the moment where you actually would go to a doctor that would actually take a picture of your change on the skin. So essentially, like, kind of the pattern here is that again, we have this predictive patterns that are actually not what we are asking the model to do, but it still is predicting according to populations. Okay, so I hope I convince you that, like, much of the behavior of our models is driven by the data and understanding kind of how the data influences the model decision making. So now the question is, okay, so what can we do about this? Okay, and the goal for today, I actually want to tell you about our recent work that tries to do something that I call like model-driven understanding of data. So essentially, what we really want to do is we want to understand the training data that our model uses, but understand it through the lens of how it looks to the model as opposed to how it looks to us. And it will become more clear what I mean by this in a moment. Okay, so essentially, I don't care about, for me, how I would categorize the data, how I would partition it, how I would structure it. I just want to know how the model perceives the data, like what things are similar to it, what things similarly impact its decisions, and so on. So it will become more clear in a moment. So just to kind of make it more concrete, this is just a restricted kind of question that you might ask, but like you can think of this basic primitive of scrutinizing predictions. So imagine you have some training set S, you have some learning algorithm, and you have some test input X. And you train your model on this training set S, you fed it this beautiful doc into it, and you got this answer. And now what you would like to ask is saying, wait, so for this prediction, what were the training images in my training set that were the most informative for me to make this prediction? Again, if I remove all of the images, clearly I will have no idea what this is. So I had to learn kind of from some of the images, like maybe from all of them, but like questions like, what are the most critical ones that can inform this particular prediction? Okay, that's kind of the question we would like to answer. And by the way, especially if you are a statistician or read some statistics, you will know that there is kind of a mathematical answer to it, or a kind of notion, a concept that captures that. It's called influence functions. And in particular, in the context of machine learning, people kind of are focused on this approximate leave one influence. So essentially, what you are asking is the influence of a training point xi on an output xj is the difference in probabilities of like the probability that I will get this input right if I train off all of my training set versus if I get this input right if I train on all of my training set except that one training input. Okay, so I just want to say how much of a difference, including this this input gap. And again, people studied it in the context of machine learning, in particular, Cole Young kind of operationalized it in some, taking a lot of, unfortunately, shortcuts because you couldn't do it otherwise, trying to approximate them. They have some issues. There was work of Feldman and Zhang that kind of have an alternative approach to do it. But kind of what we want to do here is we want to ask the question from the previous slide, but go beyond this leave one out influences, because in particular, this, if we are only thinking about the marginal impact of an input with respect to the whole training set, that's actually a very restricted notion, because you can imagine that if there is another copy of this image in there, then this influence is is zero. But actually, if I remove both of the copies, the influence might be enormous, and you will not capture that. Okay. So yeah, so can we get a bit more direct read? So again, we want to understand how the training data yields models outputs through the lens of a fixed training algorithm. Okay, so we want to go beyond this single input impact, And also, we want to kind of capture a bit more nuanced notion of whether like we got the input right or not. We really want to understand the whole mechanics of like kind of surface all of the mechanics of this prediction. And essentially we also want to make sure, because like with this previous methods, like you look at these images and it says, okay, does it make sense? It maybe makes sense. Maybe it's not. Maybe this is the right answer or not the right answer. Here we want to actually have a precise way of measuring in what sense the answers we are providing are the right answers or not, and how well we are doing on solving this task. Okay, so that's what takes us to this framework that that this talk is about. It's called data models. So what are data models? So again, data models are trying to do this data to output modeling. So imagine again, usually when like the way I deploy an algorithm is saying, I have training data, I use some algorithm to train the model, and then once I have a model, I can run inference on the particular input X. So what I kind of want to do is I want to completely abstract away, like kind of average out everything that happens over here, and I kind of want to get this direct mapping from training data to decision on a particular input. I want completely abstract away. Essentially, think of this as I'm trying to kind of, because this process like training involves some randomness and so on. I want to smoothen all of this out, average all of this out. I want to look at this aggregate effect of like how the exact shape of the training set impacts the output on a particular thing. Okay, so essentially like the function that will be of interest to me is this function that exactly like takes a particular input of interest and takes a particular subset of the training set, and essentially what it tells me like some quantity of interest about this in output X. Think of this, for the sake of this talk, that this is like the margin of the correct class. Okay, so I say like how sure I am about this being a correct class. Okay, so that's the object that we would like to kind of compute. The problem is that, remember, the dimensionality of this is pretty crazy. So we don't, because it's like if the data set is 50,000 inputs, this is 2 to the 50,000. So we can't hope to like write out this function explicitly. So what we will try to do instead is essentially study a simple approximation of this function. Okay, and essentially, and data model is exactly this approximation of this function that we will be trying to find. Okay, so how can we go about finding such an approximation? It's actually, once you set this goal, it's kind of relatively natural, relatively easy. So you essentially treat it as a regression problem. Okay, so what do I mean by this? Well, what I do is I will kind of just generate a bunch of examples in which I take some subset of my training set. I then train so essentially this is some subset of my training set, and then I train my my models on the subset, and then I kind of look at the input, or like if there is more than one input of interest, I look at the what my model outputs for that, like after being trained on this particular subset on this particular inputs of interest. Okay, that's my one data point. Then I can do another one with another subset, and another one, and another one, and this way I can kind of create this kind of data set of a subset as an input, and and the output of interest here. And what do I do next? Well, I can just now try to fit a model to this data. I want to solve the regression problem that corresponds to it. I would like to just have a mapping that, like, for given input of the subset, when again this is just like put as a subset as a mask, in a kind of I am supposed to predict what is the correct output. Okay. Of course, there are two emerging questions. The first question is, how to generate data. So how do I choose the subsets to build my my data sets? And I do it by just here we go with very simple thing. We just kind of independently at random sample each of the elements with probability alpha into this subset, and then like what class of models to fit. And this was the question that actually, like, you would think, okay, it has to be something crazy, yes, because we are kind of clearly like approximating a function that is like corresponds to training deep learning models and like all of this crazy stuff. But it turns out that you can work with a very simple choice, and it works very, very well already. So our choice of the model is actually essentially linear model. So the way our data model will be, it will be corresponding for a given fixed input X is essentially linear. So what essentially we will learn for each input of interest X a vector that has a one weight per each training point in our training set, and then here it will just be taking the mask of the subset we care about. and we kind of want to learn essentially these vectors of weights that for which this corresponding model will actually make the right predictions. So this is essentially as simple as you can imagine it be. So again, so that's what we do. And okay, so now we know what is our regression task. So we need to create like this data set, and then we solve the regression task. So the obvious question is, again, things probably should look a bit crazy to you. So the question is, first of all, like, how many samples do I need to have even a hope of solving this regression problem? And the answer for specific data set CFAR is 500,000. So it's not, it's a little bit. And how do you train 500,000 CFAR models? Well, you have to have smart students, and they build a library that significantly speeds up training and allows us to do like essentially one model every 2 seconds on a state-of-the-art GPU. You actually also can do it for Imagenet, which is much larger data set. So again, it's a lot of compute. It doesn't compute right now, but it is feasible even for a research lab. Okay, so but the point is that we can do it. We can fit this. We can solve this regression problem. And of course, the question will be like, how do we know that we succeed? Like, how do we imagine I train this data model? How would I know that I'm actually like getting somewhere? And one of the most natural way to do it is just essentially like figure out if you solve the regression problem well. So how do you do it? Well, you sample a new subset of the training set, and you compute the correct predictions, and you compute how close data models predictions came to that. And it turns out that actually it works pretty well. So if you kind of compare the predicted margin for this new data set for a given input of interest and the actual margin, again, you have to take expectations here because there's some randomness involved. Essentially, you get a pretty good fit. Actually, this pretty good fit is not only in aggregate, but it is also for individual inputs. It's actually like pretty good. So again, it took 500,000 models, but essentially like linear classifier and a bit of a lasso kind of essentially a bit of lasso regularization term, and you seem to be doing very, very well here. Okay, remember that the dimensionality of this problem is 2 to the 50,000, and so we still 500,000 is nothing compared to that. Okay, so yes, so essentially like we have this kind of behavior, and actually you can also try to test it not only on the subset trained with like a random random subset of the training set. You can also explore some non-random ones, and it also seems to work pretty well for this. So clearly we are solving this regression problem. And now you might ask, probably you are already asking for like last 3 slides here. It's like, why on earth this would ever work? Honestly, I have no idea. We just did it and it worked. There is actually a recent work by by Sanusi et al. That actually has a very nice insight about this, and this actually connects it to Fourier analysis. So essentially, like they roughly speaking, what they show is that what we are really trying to do is we are trying to compute here like the first order approximation, like Fourier approximation of the underlying function. And since the problem is noise stable, or at least it seems that it should be noise stable, then the higher order terms are not that important. And really, like the linear approximation is already pretty good. So there is kind of, we are starting to getting some understanding of what's going on here. Okay, but like we got our data models, they seem to work. Now, why were we doing it? How can this be useful to us? Well, it turns out that data models can be useful for, like to us in many ways. And actually, we are keep discovering new ways. So again, just to remind the setup, so we have this data model, which is this linear model that, again, for every input of interest, it has this vector that assigns a weight to each element of the training set. And the way you compute the corresponding value is just by taking this, inner product, this vector with mass of the subset you're interested in. So, okay, so there's a number of ways in which you can leverage this linear approximation. So first of all, it kind of allows us to understand kind of the brittleness of the models from a causality perspective, and I will explain in a moment what it means. It also allows us to have some insight into what is the generalization mechanism behind some of the predictions that the model makes. It's also kind of, it goes even more interesting. It actually produces an interesting embedding of data in Euclidean space. And finally, it actually allows us to overlay a graph representation over our training set, which we are used to think of training set as a collection of inputs. Now we put a graph over it. Okay, and I will talk about this as well. So let me dive into this, into this demonstration. So analyzing model brittleness. So here is an example. So this is a CFAR, this is a CFAR image. That's why it's so blurry, because it's kind of upsampled a bit. And you train your CFR model, and essentially it recognizes this image as a boat with decent confidence. Probably I would have trouble to get similar confidence on this picture. I'm actually very bad with recognizing CFR classes, so my students always make fun of me about that. But again, our model is great. It roughly gets the right answer, so that's great. But now there's something disturbing about this. What is disturbing is that actually it turns out that if I remove this 9 pictures from the training set, I will consistently get this image classified as an airplane. Okay, so there is clearly some brittleness here. So essentially, my correct prediction of this image hinges on this presence of these 9 images in the training set, 9 out of 50,000. Okay, in fact, this is not by far the only one who is kind of relatively brittle. There is for 1/4 of the data set, essentially you need to remove less than 0.2% of the training set to flip the prediction. And again, the important thing is that I'm not changing the labels of it. I'm just removing them. So it's not about trying to mislead the model. I'm just withholding information. So all of the prediction just hinges on this supported on a relatively small set of training examples. So that's interesting. But again, how could you have computed it? Well, you use data models. Essentially, what you did is you looked at the images that for these predictions had the highest weight, were the most influential, and you remove them. And you see kind of this way, you see kind of how much down this prefix you have to go to see the prediction flip. Okay, so you can do this kind of probing of this kind of brittleness, causality brittleness using data models. But now, how about instance generalization? Well, again, as I already said, what this model gives us, we have a bunch of inputs of interest. This model gives us, the vector that assigns a weight to every, to every image, every training image. It can be positive or it can be negative. So the tempting thing to do is again look at the most positive, kind of the training example with the most positive weights. So what you will do if you do it for these images, these are the images you get. And kind of you can start seeing, okay, so why the model kind of made this prediction. So here, kind of you would say, okay, there's some feature similarity. There is a lot of pictures in the training set that kind of are similar and are also airplane. So kind of you expect that this is how the generalization happens. Okay. However, here you see something else. Is you see essentially there is a copy of this image in the training set. So by the way, you will discover a lot of that. Our data sets suck. You get a lot of identical copies, or essentially just things in just under the different angle, or here you have the train test leakage, which you should have the same track, just different color. And you can kind of find the benefit. You can just find the same object, just photographed from different sides, because again, this data was scraped from, this is from Imagenet, but was scraped from social media. So someone had a series of photos of the same object that they liked, and now you kind of put all of this in your training into your data pool, and then you do the random split of some of them randomly you assign to the test set and some of them to the training set. Well, guess what happened? That some of them are, some of the copies of the things you are testing on are in your train set. Okay, so these are the positive guys, but there are also negative guys. So you can look at okay, what are the guys with negative thing? And here you see exactly what might be misleading the model about the data. So essentially you see that there are kind of this very similar images from the incorrect class. My favorite is this one, which by the way, this is a turkey. You have to trust me on that. And here, this is actually a deer next to a girl, probably with a blue balloon. So essentially, the model is essentially matching this blue to this blue, and that's what is kind of misleading. Okay. So that's a kind of instance generalization. So now let's talk about the embedding. So again, for each input of interest, I get a vector of of numbers. That's an embedding into 50,000 dimensional space. So essentially, it's actually, you can make it because we make it in the regression relatively sparse. So you have this very high dimensional but sparse embedding of all the inputs of interest, and kind of this and you can get first of all a similarity metric out of this, because but it's interesting similarity metric. It says inputs are similar if similar training points act similarly on this input. So again, you can see how actual similarity might come out of it, but it's a different similarity with what you would get from for instance, looking at the representation of the model. Okay, but that's not all. It's saying, okay, if I have a very dimensional sparse representation embedding, how can I make it less, less dimensional? Well, I can use PCA. Okay, I can just like form PCA of this space. Well, when you do PCA, a very cool thing happens. So essentially what you are having is you are getting kind of the PCA directions like that, like, this is my favorite, but they all are like that. Like just here is the PCA direction that corresponds to, well, in the positive direction, it's planes against the sky. In the negative directions, it is birds against the sky. Similarly here, you have horses, from the side against the grass. Here you have, you have dogs, from the side against the grass. My favorite one, oh, we cut this. So essentially, like there is on one of the sides is a, I think here there is a, there is a mislabeled horse that is actually a dog. So it will be here. Sorry, so there is a dog, like there is a picture of a horse against the grass that was mislabeled as a dog. So it got put here as opposed to here. But you can see that clearly that like kind of it is kind of figuring out these features. Okay. And the interesting thing also is that if you do a PCA of a normal model's representation, it will kind of essentially like after first, number of classes, number of PCA directions, like you will get most of the explained variance there. Here, the explained variance actually has like very, very long, tail. So essentially like this, you have this very like richness of information that is kind of inside this representation. So even the top direction is like 0.1% of the total explained variance here. Okay, so that's cool. And this brings me to the last kind of aspect, which, by the way, if you know my past, you know that this is the one that I was the most excited about. So I used to work on graph algorithms, in particular spectral graph theory. So essentially now you think the following. Okay, so for every input we get, we are getting a vector of like number of training example size. But now, when I talk about inputs of interest, I could also take the training examples could be also output of interest. So imagine that like I take one training example and I treat it as an input of interest, and of course I never include it in the training. But other than that, I do exactly the same as I would do with the test example. So I can produce this kind of vector of dimension like size of the training set for each of the training points. So essentially, if I stack these vectors together, I will get a matrix that is training set size times training set size. How about I will treat this matrix as an adjacency matrix? What will happen? Well, I will get a graph. Right? It just will be a graph. It turns out that this graph encodes a lot of similarities that you would see. So essentially, like, what you can do is you can kind of look for connected components, and they kind of will correspond to meaningfully similar subpopulations. Okay, and essentially you can read a lot of the structure of the data from this graph. In particular, now what you can do is saying, hey, for the like three decades, we work on algorithms for doing clustering on graphs or kind of doing learning from graphs. Well, you can now apply all of these algorithms to that. So we did not do all of that yet, but we did some simple things. So for instance, we just said, okay, what will you get? You want to find isolated subpopulations in your training set. Then how about you just cast it as a mean cut problem with some ILP solver, because we don't want to deal with pesky rounding. And this is the kind of things that you are getting out of that. These are the minimum cuts that they're finding. And again, what I find striking about this is not that, okay, you can find this image, by the way, there are almost copies of each other, but this is all completely data-driven. There was zero human intervention in anything. Just all of this is literally take a PCA or take this, vectors and run some algorithm. Like it's complete, there's zero human kind of intervention happening here. All of this is completely data-driven. Okay. I think it's time for me to wrap up. So let's just do that. So there's a couple of takeaways I want to kind of leave you with. So first of all, is I really view that data is the most critical aspect of ML, and an underappreciated one. In particular, we really need to develop both a toolkit, a practice of kind of learning, recognizing what kind of learning biases our data conveys and how to modulate them. Like I think we are not doing great there. And data model is just a framework that is like what I call this model-centric data understanding. So again, you kind of try to learn this data to output mapping using regression. It's actually turns out that this simple linear instantiation of this framework works surprisingly well. And you can again have this like a variety of primitives that that this framework enables. Again, I just have shown you some, but since then, in my group already, like we have a bunch of other things. You can use it for model comparison to understand how different architectural choices or training hyperparameter choices impact what kind of biases your model has versus doesn't. You can you can understand evolution of training and how the model is learning. So essentially, like, it really seems that this is kind of this, this new, like the microscope that allows you to really look at different dimensions of our standard tools and getting new insights there. So, yeah, so that's the question. So what other insights can we produce here? And, the one thing, especially given this audience, I want to say is that, like, all of I did so far is, I would say, it's principled. It's kind of, there is a hopefully clean conceptual picture, but all of this is purely empirical. Like, there is literally, like, except the paper I mentioned, there's no math that even tells us exactly why does it work, when it will work, like why 500,000 is the right number, like why not 1,000,000 or 100,000? Like, what's even happening? Like, even the asymptotics of some of these things are not known. Again, I expect that if I was more trained in statistics, maybe some of these things are known, because this is like linear regression. So something that statistics kind of, study to death, but my modest attempts to find something relevant actually failed. So if some of you have some idea, oh, this is just, no, this problem should look there, I would welcome this kind of pointers. So that's all I have to say. So I'm happy to answer questions.
Ladies and gentlemen, we have time for questions, comments, suggestions.
So I remember at the beginning you were talking about this sort of one of the foundations that in some of these other models for explaining training data, that you could have a situation where you have two very similar or identical samples, and the influence would look like it's zero, but it's actually
yeah.
In these data models, it seems like you would have like a degenerate solution, because like any arbitrary linear combination would be your weight. So does it really fix that problem?
Yes, it does. So that's a great question. So the question again, imagine I have just 2 copies of the same image in my training set. So first of all, if I just use leave one out influences, then the influence of either of this will be always 0, right? Because essentially, like, even if I remove one copy, the other copy will stay. So essentially this would be the same. The question is what happens with data models. So what happens then is that essentially, like, the data models tends to, this is more of a, you are right that in principle you could look at the degenerate solution, but like here you essentially spread the credit evenly. So essentially you will find that, and we tried it explicitly, like if you do copies, they will exactly get the same influence. Essentially they will split influence among themselves. Yeah, yes, because like we are averaging this out. Essentially what happens is that we are averaging this out on over many rounds, and in some of them, one of them will be more influential because it probably depends on where in the batch it kind of falls. So essentially that's why it's kind of tends to to even out.
A couple of questions. So one is think about this linear model.
Yeah.
Between the data model on the linear model, would it be covered or similar to the different contribution to like this, patient inverse of times gradient? Would it converge analytically?
It should. I did not try, but like, yeah, it will be exactly the same thing there. It's like, because you are just like essentially like your function will become okay. We need to work the map, but it should, yes.
So question is the sensitivity to the parameter, the probability that you're counting. So like, let's say I like use in testing the data model, how that is work.
Okay, so this is actually like 2 questions in one. Very, very efficient of you, Sohail. So one thing is that, first of all, like, what is the role? Like I said, okay, we are using some alpha in our training. Essentially, like we kind of sample each sample independently with probability alpha to be in the subset. Like, why didn't I fix this value of alpha? Well, the thing that we discovered is that actually, like, different choices surface different behavior of the model. So essentially, like, for alpha being large, which means that most of the inputs are usually in, kind of you capture more kind of the inputs that kind of have by themselves have a lot of influence. Like essentially, like things that kind of essentially you look at things that kind of, I would call it like memorization like behavior. Essentially, like that essentially that these inputs are so unique and so important for some input, so output, that like all that matters is whether they are in or not, and it doesn't really matter what other pictures are there. When you work with a small alpha, you are kind of zeroing in more on the behavior where kind of the large, like essentially like you can then read off situations where there is kind of relatively large subpopulation supporting some prediction, and then you can kind of realize, oh, these are the important guys, because most of them will be gone, so the ones that are left essentially like you will be able to capture the influence. So that's why kind of you might want to you might want to vary the alpha, and actually, like, depending on, we also apply to data poisoning and other things. So then, like, you want to play with alpha depending on the application. Now, your other question, if I understood, was essentially question. Okay, so assume I fix some alpha for my training, and I want to evaluate, and I use a different alpha. So I already referred to it. So it actually works pretty well. Like, you see that there is a bit of degradation in performance, but not actually much. It actually generalizes pretty well across alpha, which was surprising to us. So, but that's that's one of the examples when I said that it actually works out of distribution as well. So essentially, it's actually even like training with one alpha and testing on the other still works pretty well. Like, there is a difference, but it's relatively small.
So this is all for supervised models. We thought about this for unsupervised systems, or is that
well, yeah, funny that you ask. So essentially, like, so yeah, so again, there's nothing, it's really not about supervised learning about, it's just saying I have some function that, like, given input, like there is a number. So what we did, so we can apply it to anywhere, and what we actually did, we applied it to transfer learning, which is still like, we wanted to understand essentially, like, how, composition of your pre-training set impacts in, like, the quality of the features that you are learning for transfer learning. So essentially, then your objective can be, for instance, like performance on after fine-tuning on a bunch of tasks, and then you can kind of get the influences there. Again, it's still at the end of the supervised question, because again, you need to have some measure of, like, there has to be a number at the end, but it doesn't have to be a class. It can be something else. So we did apply it to transfer learning, but you could probably do it to other stuff as well.
Yeah. So I think discuss, like, the relationship of this those data models to Shapley value. Because the association that if you fix alpha to be 0.5, then what would you do with the linear model actually regressing the
Okay, so again, funny that you ask, because we are kind of working out the relation to Shapley. Like, I don't think, like, unless I misunderstood something or I'm not seeing something, I don't think this is that simple, but maybe I'm missing. It's just like, the point is, so the Shapley value, by the way, and this is kind of the question of kind of, imagine there is okay, so this is a concept from game theory. Yes, imagine there's a bunch of cooperating players that kind of contribute to some outcome, and then this outcome ends up with some payoff, and then you kind of, want to do I attribute, like, how do I apply to the players proportional to the contribution? And that is essentially a very, intuitive and principled way of, formalizing what an optimal kind of split, like what properties it would require, and then actually it turns out there's only one way of doing it to satisfy all of this, all of these properties. So this is a concept from game theory. Now, it actually was used very successfully in machine learning as a way to try to do feature attribution, okay, in which you kind of can ask, oh, I have these features, and kind of I made this prediction, which is like the payoff, and like, how should I attribute, like, essentially, like, assign the kind of the credit for this prediction among the features. So first of all, like if that's kind of, so the Shapley value interpreted, like, it operates in the feature space. Yeah, so I'm just saying traditionally it's there, but you can also apply it to training set, and in some sense it's kind of is related. I don't think that it's as simple as you think, but maybe I'm missing something. I'm happy to discuss it afterwards. But like, this relationship in particular, again, what you need to compute Shapley value is exactly this kind of counterfactual experiments, saying, oh, imagine I only took this subset of, in this case, training set. What would be the prediction? So there is a relationship, but I don't think it's as simple. But again, maybe I'm missing something.
Another question?
There was a consistent 500,000. What was the significance of that? So throughout all the models,
Oh, no. So, okay, so there were two fives and some zeros afterwards. So there was 50,000, which is the size of the training set that, like, we did most of these experiments on. So then that's the size. So essentially, the dimension of the data of this vector that you learn in data models are 50,000. The space is 2 to the 50,000 and so on. There was also 500,000, which is like 500,000, is the number of kind of data points that you need to create for this data models regression problem to get good fit. So, again, and this number is empirical. Like, like, the question is like, why it's 500,000? Well, again, 400,000 also works, and 600,000 would also work. But like, it seems that the 500,000 is roughly the right number. So why this is the right number? So that's where the numbers came up. one of the projects that I'm trying to ask my students. For some reason, they are busy with other stuff. I don't know. I don't know who is giving them all projects to work. So yeah, I will remind my students that they are supposed to do that. Yes, that's exactly the interesting question. It's like when you look at the prediction on adversarial examples, what are the influences that inform that? Like, yeah, maybe you will be faster than my students.
There's one thing that I can think of, it's kind of hard to do theory for this kind of thing. One thing that's kind of theory verse that I can think of that I can relate it to is kernel methods.
Yes.
Kernel methods, you start with some model, you pick a kernel in there that measures the similarity between images, and then you do many lines of, mathematical derivation. Students in my class seem to 8. And then you end up with all this complicated math, you use, the formula that says that the prediction you're going to make on a sample is a linear combination of the predictions you got. Predictions come from the data set with weights, and the weight that you assign to each data point is given by the kernel similarity between the inference point.
Yeah.
Point, right? And so this feels a lot to me like a kernel method, right? You learn some sort of kernel. But there's one nice thing about handcrafted kernels, you can then add more data later. Right? Whereas here, because the way that you learn the kernel is I guess my question is there a way to get some of these other nice kernel properties? Like, can you add, but I'm just want to add data later. I guess subtracting data is sort of right.
Yes, so that's a great question, and that's something we are thinking about. Like we definitely so one operation that we so adding additional training point is a little bit annoying. So that's definitely true. Even adding additional input of interest if you didn't save the models that you actually train for the subsets. So we are kind of thinking, we are exactly like playing with how exactly like from around the kernel methods to kind of see if you can get something like more versatile here. The one thing that we did is, even though it's not clear to us, like I guess subtracting, we didn't think about it, but like probably it should not be too hard. I know actually it might be hard as well. So I don't know. The thing that we did do is actually like subtracting data models from each other. So essentially, like imagine you have two data models corresponding to two models, like to two different training algorithms, and you kind of try to understand exactly like how impact of like large learning rate versus small learning rate have, like in what way the picture of the influencers changes. So essentially, then you have two data models for this like two different learning algorithms, and then you can kind of compare them in some like a bit of linear algebra to get this kind of residual data models that kind of surface essentially the training examples that are have the most variance when you go from one to the other regime. But that's the best we could do. But yeah, we are thinking about if there is some kernel behind this. Like, does it mean that there is some again? To me, the surprising thing is that like 500,000 samples and a linear model seem to do pretty good job at that. So does it mean that there is some inherent like that you are really approximating now? No.
How do you control for the variability of a cross classifier? Because they will also do different predictions to just randomize the weights differently.
Yes.
And then train. How do you control for just the variability you get from data set selection and not the variability you get from FD ordering or initialization?
Yeah, so this is good. Again, the way we do it is that, okay, so the right way to like the proper way to do it is just for each mask you choose, you train many models and average out predictions. So we don't do that. For each mask we train only one model, but then we do many masks. And it's a good question that I literally discussed with my student 3 days ago. Is exactly like there has to be some magic happening, that because these things are pretty stable, so that even though I'm solving this regression problem for like with only one model per mask, somehow this like there is also this averaging it out across across one mask. But that's a great question.
I use different initializations for training too. Do you fix
initialization matter, like, so that's the point. It's like, so what is fixed here is the training algorithm, because and this is exactly like what we kind of this upcoming paper about this like impacts of even small changes in the pipeline. Like we show that this actually changes this picture out. Like we didn't play with initializations, but again, changing learning rate, changing the data augmentation you use, and there was one more that I forgot. But like,
but do you know, is it fixed initialization time for the network that you train there?
yeah, so it's always the same initialization. So no, like it's the same initialization scheme.
Different initialization though.
Yes.
Okay.
On average, if you compute these weights and so on, you say, okay,
if all the weights are sparse, there's like these 9 things that if I remove that setting, is that like the norm, or are most things stable and then there are 2 outliers?
Yeah, so I say like for around 25% of the training of the test set is kind of less stable. Like it depends what is like, meaning if I removal of 0.2% of the training set, it kind of flips your your prediction. Is it is it stable or not? Like sounds like small. On the other hand, it's like 50,000 examples and it's like so many classes, so it's unclear. But like again, you definitely can ask for this profile. Like definitely 9 sounds like this is a bit too few. Again, I don't remember the numbers, but like I think it's more brittle than we expected, but I wouldn't say it's like horribly brittle.
Well, it's just a counterfactual question. Like, if you remove these 9, and maybe that's those are the 9 that resemble the 10 of this year. So maybe now all of a sudden you don't have anything that represents the material of the plane.
Oh yeah. So that might be as simple as that. Like, but even then, that's concerning for you. It's like if that's the only boats that you have seen, like you have in your like of this type you have, then probably something is wrong. Yeah, it could be very simple reason for this 9. Just like we don't judge, it's just like we're saying this is the 9. Is it for good reasons or for bad reasons? That's for you to decide. We're just telling you, this is the fact.
So maybe I will cut in a little bit because I'm told that the food already.
Oh.
And there's some standing between this.
Yeah. 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 I appreciate that your concern. Completely altruistic concern.
So, ladies and gentlemen, perhaps we can take all the discussions to the room across the corridor. The IT that we follow and we involve a minimal amount of feedback, not